from CBase and InvokeX use that structures quite a lot. So again, our objective is to find out exactly for each method or for each property which exactly function is using, so we can analyze that function and see if that function is actually allocating a controllable string or other stuff. Obviously, this is very useful from an auditing standing point because you can audit all the setter and getters and methods from the elements. So basically, each pointer on that string table has a pointer to this structure, which is the associate B table structure. This holds another pointer to the prop description. This is basically the structure that holds all the information of each method or property inside an element. And what you see here, for example, you have the hash, which is a hash of the string, which is used to find the string fastly through that structure. And then you have a couple of index in here, which is a byte long. They are indexed into a big table. The function one is the one that has the index for a function table, which is the one responsible for actually doing the getter and setter or calling or the actual method. And the UID is related with the UID of that object. So it's like the body. It will be the UID of the element object for body. And then on the property description, you have the actual name or an alternative name of the property. And then you have a lot of flags we are not going to explain. And you have this keyword here, which is called WIMP function, which is basically an offset to another big table of functions, which are the invoke functions. Invoke function, basically, what it does, we can see here in code, which is easier. There, basically, we have first the index to the UID, and that will give us the actual UUID of that element. And then with that UID, we do a query interface, which, as you guys has already said, the query interface is the one that returns interfaces. And so we're going to get the actual interface of that element. Because remember, the getThisID and the InvokeX are both a very generic function for all the different elements. So if they are adding new elements, instead of writing the raw objects, it's just adding those stuff there. And then we have a function index, which was on the WIID index function. And then, first of all, it actually calls an invoke function, which is the one that gets all the parameters correctly. And depending of which type of property it is, it's going to have a different invoke function. For example, if it's going to be a string, there is invoke functions called putString or putVariant, etc., etc. Or depending how many arguments it has a completely different invoke functions. The invoke function basically just transform all the elements in order to actually call the function that is in charge of this setter and the getter or the method. And the actual function that is going to do all the setter and getter is the resulting from the objects from UUID and the function index. The function index is basically an index to the B table that allow you to get into the function. Now, all that works just to get string allocation. So that's how Explorer are these days, hard. So basically, you end up in this function, which is, as you can see, a function that is allocating from the process heap, which is the default heap, and it's allocating the size that you're sending. And then after that, it's doing a mem copy for the new allocated memory, just like it is. It's not copying like the the length at the beginning of the object. So that's helped us to exploit this bug. That's how we did it. But there are actually easier ways by doing dynamic analysis, which is basically what we actually did too. We create a small immunity debugger script, which we are going to release at some point, which basically do very simple stuff. First of all, it set a hook on getThisID. That allows me to obtain the number of the name of the property and the ID of that property once obviously the function is being called. And then whenever InvokeX gets triggered, which is the actual function that is going to call our method or our property, we set up at the beginning of that function, we set up the allocation and the allocation hooks. The RTL allocate heap hook was going to give us the size of whatever is allocated during that method of property. And then we have RTL free heap, which is actually the one that's going to free that memory. And finally, at the end of invoke X, because basically we are a breakpoint at the beginning of invoke X, setting the hooks with all the allocations, and then we are setting a hook at the end. So whenever that gets triggered, we set all the allocations and the allocations at the end of invoke X. We unset all those hooks, and then we have like a nice list of things that happen during that invokes, which is what we're looking for. And basically, in order to test it, we just create a small script that basically loops over all the properties on an object and just put as random string. And that's what basically we found. Like just by basically or randomly passing the properties with a string, you get, as you can see here, this is the actual property that's being called, hidden. And then you can see that this property is actually allocating two memories, 1 and 2. One of them is being free. And then basically we have at the end of invoke X a small script that's tell you if a memory leak was found or not. It's not a real memory leak, but it's still something that during the life of that invoke X or that call to the property of method was allocated and not deallocated. And so basically we can see that this allocation here of a size of 18, which is based on our string, it was actually allocating a string, and as you can see, the first few words are our control. This is in Unicode, but you can easily change it into ASCII. And so we did it with all the different properties, and we know now how we can potentially, do an allocation of the exact size that we want. So now that we have all the elements, the exploitation is very, very simple. You have first, we free the object, an object that we now understand what it is, and that we can decrease at the moment we want. That's the first moment. Then we allocate a chunk through the DOM properties. This is how use after fish should be being done nowadays. And I know there are people doing that. It's not like rocket science, but just a way to show how it works. And then finally, you use the object, which is now under your control. You control the B table, you can use it. Now, hit tray now makes sense. Like you can now hit tray and point it into a place where you know that the hit tray will actually gonna be there, not just randomly pointing to something that you might control or not. So the second fact of the day is winners use hit tray consciously. I mean, it's not bad to use hit tray, but you have to use it understanding what's going on. So this is like a bonus slide. Basically on Internet Explorer 8, they fixed the common hit tray. And basically if you do that, I think Skyline was the first guy that made that hit tray. If you do that, it won't work. So basically when we start doing Internet Explorer 8 exploits, we start like thinking, oh, well, how we can allocate and do a hit tray by doing like circular memory leaks and all kind of complex stuff. And then in the end, it was very simple. We were just, instead of using directly a string, we were using a reference to the first entry of an array and works perfectly. So that's what we are using. And there are many ways to do it. I hope they don't fix that, but if they fix, there are other ways. So how do you do it in a non-traditional way? How do you exploit use after free in a non-traditional way? And basically what we came out with is object replacement. But I didn't see it on the wild, but probably might be some people doing it. Basically, instead of just replacing it with a string, we're going to replace it with a different object of the same size, but with a different B table. It's not easy, but it's possible. And this would allow us to be more precise because we are not just jumping into a random hit tray. We are actually using another B table for different stuff. And the interesting part is that either we'll be able to get direct execution or we will be able to change the primitive. And that's a good thing. And I guess what is more important about this technique is that you can change the primitive into an info leak. And nowadays, like every exploit needs an info leak. I mean, even is a client side, and info leak is the big part of an exploit. Especially if you want to do it APT, if you don't want to fill that guy memory with like 500 megabytes of memory of a heap frame. So you have to be precise. So in order to get also the info leak will allow you not only to obtain information on the heap, but also will allow you to obtain DLLs and then do the return to libc or ROP, etc. So info leaks are now a big part of every exploit, especially if it's a new Windows versions. So in order to exploit use after free by replacing an object, the first thing you want to do is to identify the triggering function. Now, the triggering function, I mean of the original object. So you are freeing an object, which in our case we were doing an element. Now I need to know which things are the actually, which methods are the actually ones that will allow me to actually trigger my modify B table. And once you identify all the different methods that you are allowed to, in my case, I was doing through JavaScript, so I have to try to find out the many ways I can do from JavaScript in order to, for the same object, to get different functions, because then we're going to replace it from something else. So we need to find out not only the different ways to exploit it, but also the different type of arguments and the amount of arguments that I am actually receiving on the original functions. So in the case we were doing TROF, and TROF have like get this ID for example, add ref, release, those things I was able to trigger it. So that gives me what is called, or we call it, a trigger offset. A trigger offset, which means that it's an offset from the beginning of the B table to the function. So once I know the trigger offsets, so this is, for example, an example. Now, in my this is a version of of a trigger of the same bug, the EAPR bugs, and basically it's called an ECX plus 1C. 1C is actually get this ID. So now I know that from a JavaScript I'm allowed to call get this ID, and I know that 1C will be my triggering offset. They will be important, and as many offsets I can find, the more functions I could be able to later replace. So basically, these are the finds that I found by trying to replace. Obviously, add ref, which means going to increment the counter. If I just set to a property, this is an element dot whatever, and I set my object to that, it's actually going to increase the reference. Then by doing delete the objects, I'm going to actually release the object, so that will call the offset plus 8. Get this ID by just calling whatever, or trying to get any property or actual method. It's going to call get this ID. Then I have delete member name, just by trying to delete whatever. It doesn't matter if it exists or not, because that's usually resolved in runtime. So by doing delete p dot some property name, I'm going to actually call the offset 24. And then finally, this the get next this ID, which is basically the way you usually loop over all the properties. And that actually got the offset 34. Now, once we got all the offsets, we need to know if we have those objects, we have something that we control. Can we control the arguments that we are sending to that function?